This is a talk on gravitational allocation to uniform points. It's with Nina Holden, who's a student at MIT, and Alex Jai, student at Stanford, and you really couldn't ask for better collaborators. Before starting on the topic, let me use my pulpit to recommend to all of you speaking, especially though, I don't mean today, but in general, when you give talks, especially with junior co-authors, I've learned this trick of putting the co-authors' pictures, because it's so easy to forget when you have like a more senior speaker and he has a junior co-authors who maybe did most of the work, then it's so easy to forget their names. But we've been selected to remember faces more than just names that flash by. So with that, let me start on the topic. And it's a topic that goes back a long while. In particular, I've been fascinated by it for already 20 years. So it's comparing matchings in the plane, and later we'll see allocations in the plane, different kinds of matchings and allocations which will have a bipartite nature. So let's start with matchings. And so we're going to take a manifold without boundary in the plane, but in fact we'll focus just on two examples, a torus and a sphere. And there won't really be difference in the theorems we can prove in both cases. So I'll switch just for pictorial reasons between the two. But here you have, so the example here is you have a torus, so a square with periodic boundary conditions. We're going to make it have area n. So this is root n by root n square. And then we have n blue points and n red points thrown independently and uniformly at random into this torus, both on the right and the left. Oops. I'm getting this. Okay, and both on the right and the left. Now, and then we're trying to match the blues and the reds. Now, what you see on the right is the optimal matching, minimizing the total length, or equivalently the average length of the matching. And this has been studied intensively since the 80s, and it's well understood. So in 2 dimensions with this normalization, the average distance in the optimal matching is order root log n. That's a theorem of Aitai, Komlos, and Tusnadi. I'll state it again later. So here the average is root log n in this root n by root n square. Now what you see on the left, calling it the stable matching, it's also the greedy matching. So the simplest construction of what you see on the left is this. You take a blue and red point that are closest to each other, match them, take them out of the matching game, and now repeat. So each time take the 2 unmatched closest blue and red points and match them till you've exhausted all the points. Okay. Now, why am I calling it stable? Because it has an alternative construction, which is the Gale-Shapley stable marriage. So each red point prefers the blue points according to their distance. So it prefers to be matched to close points. Similarly, for the blue points, they prefer to be matched to close ones. And then there is a notion, whenever you have two kind of preference orderings for both sides, then Gale-Shapley ensure that there is a stable matching where there's no unstable pair. So an unstable pair are blue and red points that are not matched and prefer each other to their matches. So there always is a stable matching. In general, it's not unique. In this setting, where both sides use the same metric, it's unique, and it's the same as the greedy matching. So with that kind of background, so here you have that greedy matching. It's simpler to define than to construct the optimal one, algorithmically faster, but it does worse on the measure of the average, but we don't know how much worse. So the bounds here are very far apart. So the lower bound is still root log n, the upper bound is about n to the quarter. So one open problem I'm emphasizing now, I'll emphasize again later, is understand this matching. Now, the optimal matching does have a polynomial algorithm, which is somewhat sophisticated, also classical, but we're going to look at somehow simpler algorithms to define more local and focus on the gravitational one that you'll see later, or precisely an online gravitational algorithm. So, by the way, these pictures are due to Ander Holroyd. Okay, so we're going to move from matchings to allocations, and here is the formal definition, but here is the picture of a different allocation, again pictured due to Ander, which we studied long ago, so also with Chris Hoffman. So what you have here is you throw n points again in the torus, and we want to allocate to each equal area. So that's what a fair allocation is, and it's kind of analogous to the matching problem. So this allocation is created by each point growing a sphere at unit rate, a disk at unit rate around it, and each point acquires all the area it reaches first until it is sated, until it gets its fair share of the total. And then it stops. So some points, like this one, are very lucky and they just get a sphere, a disk around themselves. Other points are hemmed in, and so their territories become disconnected. So if you look, for instance, at this point down here, right, it is hemmed in, so it starts to grow, but the area around it is acquired by other centers, but it keeps growing in the background, and eventually it gets its fill way out here. Okay, so everyone will get a territory which is equal in area, but some of these territories will be disconnected, and it's an open problem here also to understand, like, what's the average distance traveled between, if you take a typical point and look how far it is from the relevant center, what's the average distance that's open with similar bounds to the matching problem. Okay, so this is the formal definition of a fair allocation. So we're going to have a set of centers or stars. We're going to call them stars, these n points. And we'll have a function from the manifold. So we're going to switch from the torus to a sphere, but everything applies in both settings. So now we're going to talk about an allocation on the sphere. So from the sphere to this, so it's just a mapping from the sphere to the stars, where the pre-image of every star has the same area. So here, if we normalize that the area of the manifold is exactly n, then it means that the area of each pre-image will be exactly 1. Okay, so we'll tend to do that. And then there could be some points that are just unmapped, and then we'll just formally map them to infinity. We have to ensure that that's a zero measure set. Okay, so that's definition of fair allocation. We'll want a fair allocation which is efficient in the sense that points get allocated close to where they started. Okay, and some of you who get the notices may have seen this fair allocation on the cover, and so the main purpose of this talk is to tell you what this is, and it will also be related to Michelle's talk in the afternoon. Okay, so we're going to be interested in an allocation rule. So not just for a specific set of points, but given any set of points, how to allocate fairly to them. And we want the allocation rule, which, as I said, is efficient. So we want to kind of minimize for, on average, the distance from x to the point it's allocated to. So there's, again, a very sophisticated theory of optimal matching and also optimal allocation that is a special case of transportation. Here, our focus will be on kind of near optimal allocations, but that can be constructed in a very intuitive and as local as possible way. So this is the scheme of gravitational allocation I want to now define. So we're going to start with the gravitational potential. And since this is a two-dimensional object, it's going to be a... So here I have to choose either the sphere or the torus. I'm going to describe it for the sphere. There's an analogous thing for the torus, and other manifolds. So let's start with the gravitational potential, which will be, so the harmonic function in 2 dimensions, which is function of a distance, is a logarithm. Here it's a little bit different because we're working on a sphere, so it's a 2-dimensional object in R3. The distance we're using here is the distance from R3, not the spherical distance. And u of x is the sum over the stars of these logs. So that's the potential function we're going to use. And then the force field will be minus the gradient of the potential, except there's this s here. So if you just formally differentiate, look at the gradient, it will point inside the ball. So we don't want points to go inside. We want everything to stay on the sphere. So given wherever this vector points, we're going to always project it to the tangent plane of the sphere. So we're going to get a force that keeps things on the sphere. So that's this subscript s. And then once we've defined the force, we get flow lines via this ODE. So given the starting point x, we have a curve yx of t that starts at x and satisfies this differential equation until some stopping time tau x. And this tau x represents the time that the particle gets swallowed by a star. So this is just continuous gradient descent, if any optimizers here, continuous gradient descent for this potential function starting from x. If you want to see important notions for us will be the basin of attraction of every star. So all the points x that are mapped to z, to the star z. And then the terminal point psi of x, this limit is just psi of x. So it's z if x is in B of z, and infinity if x is not in the domain of attraction of any of these points, of any of these stars. Any question about this definition? I mean, this is the star of today's show, so or at least this hour's show. So here's a little picture of a local patch of this potential. So we're not drawing it over the whole sphere, just think of a small patch. And you see that it has the potential, is minus infinity at the stars. And so you can think of this gradient descent as for any starting point x, put a pebble on this surface and see where it's going to roll. That's, where this mapping psi of x. So I guess the point here is that unlike if you go to the first allocation I defined, there it was kind of built in that it's fair, right? Because every point stopped when it got sated. Here, we didn't say anything about equal area in the definition, yet the domains have equal area. So the principle behind this goes back to work of Moser et al. From 1990, but each particular case is a little bit different. But I'll explain this. But let me just tell you a little helpful story. So I gave this talk in the Math Congress in Montreal. That's where that picture on the notices comes from. But before I was allowed to give this talk, Frank Morgan, who was handling the abstracts, I sent him the abstract and said, "Sorry, I don't believe you. You have to, convince me that what you're saying is reasonable before I can publish this abstract." And he said, "Well, what about?" So that's actually been very helpful because I incorporate now his questions into the talk. So he sent this configuration. Well, what if I have one star in the North Pole and it's hemmed in by a bunch of stars? So if I then apply this gravity, clearly this star is going to get less area. And I had sent him back this picture. So it's actually, it gets its equal share. And even points here that are closer to these stars than to the North Pole star, they're going to travel here because the gravity from these two will cancel and it's just going to travel through this. So this doesn't show why it's equal area, but at least it shows why there's no contradiction in this picture. But that wasn't enough. He asked, well, what about if I have a point on the South Pole and all the rest are on the northern hemisphere? Right? Surely this one is going to get a far bigger region. And it doesn't. It gets equal area. And even points here that are closer to the South Pole, they get swept up to the northern hemisphere because all these points in the northern hemisphere kind of are banding together and pulling a point from here all the way up. So there's so this is the most technical slide of the talk. This is the one-page proof of why indeed you get equal area, and you have to remember the divergence theorem. So the divergence theorem or Stokes theorem on the sphere will tell us that on a domain, and we're going to use this the basin of Z0. So there's so on such a domain, and we're going to use the basin of one star Z0. If we integrate the we're going to take the force, remember, is minus the spherical gradient of the potential. So if we take the divergence of that, then the integral of the divergence over the interior is the integral of the force times the normal on the boundary. So that's the divergence theorem. Remember, the force was minus the gradient. That's why we have this minus sign. Okay, so this is a version of the divergence theorem just on the sphere. So this has to be the spherical Laplacian. So you take the divergence of this spherical gradient. Okay, so we write down this is the divergence theorem. And now I want to assume the area of the sphere is A, not necessarily N, just to separate N, the two meanings of N here. So we're going to take a sphere of some area A. Now, what is this Laplacian? Well, if you take one logarithm, if you're doing in the plane, the Laplacian of a logarithm is just a Dirac with this constant in front, 2 pi times a Dirac at z. This is Laplacian in the x variable. But because we're not in the plane, we're on the sphere, there's a curvature term. And, okay, this is a calculus exercise I'm not writing out. But the spherical Laplacian of a log will give you this term you're familiar with from the plane, with the curvature correction, 2 pi over the area. So if area tends to infinity, so the sphere becomes flat, and this term disappears. So if using that, then the Laplacian of the potential is just going to be 2 pi times the sum of these Diracs over the star minus 2 pi n over a. Now, if you look at these regions, maybe I have a picture of this. Yeah. So if you look at each of these domains, on the boundary, the force has to be tangent to the boundary. It can't have any component in the normal direction, or this point would be pulled inside. So, for points on the boundary, the force is orthogonal to the normal. So this part is 0. By the way, I write this Laplacian. This is a distributional Laplacian. So in this sense, close to Gurov's talk. So the force times the normal, the force is orthogonal to the normal. So this integral is in fact 0. So this integral must be 0 as well. And if you integrate the Laplacian here and write down that that's 0, what do you get? Well, in a basin, there's just a single star that's in the basin by definition. So this part just gives you 2 pi. And this part gives you 2 pi n over a times the area of the basin we're integrating in. This is just a constant. So we get this identity, which we can solve for the area of the basin is just a over n.
This is black magic. Do you have like a physical idea why this should happen? What is the intuition?
After physical ideas and black magic are actually very close. So you just have to get used to it, and it will feel natural. But we do have another proof, which is equally mysterious at first sight, and okay. So So that's why it's fair, but it's interesting because it's also efficient. So the expected distance traveled is going to be from x to psi of x is going to be a constant root log n. So again, the normalization is we're taking a sphere of area n. The same thing applies for a torus of area n. And this is in fact optimal. So except for the value of the constant, any fair allocation on the sphere will have to have at least this expected distance traveled. So we're saying gravity is efficient way to get, yields an efficient allocation. Okay, so the code for these pictures was first written by Manju Krishnapur and then modified by many people. So here you'll see the pictures for different values of n, and you'll see they kind of change because as n grows, the domains get more elongated. So this is for 750. Now, a little background about related work. So the first kind of work of this nature was also in the plane, but was not to uniform random points, but to the zeros of a Gaussian entire function. So there's a unique Gaussian entire function, unique in distribution. I'll be more precise in a moment. There's a Gaussian entire function whose zeros are translation invariant. So the function itself is not unique because you could multiply by like a function like e to the z, and but the distribution of the set of zeros is unique up to scaling. So if you have any Gaussian entire function whose zeros, whose zeros are have a translation invariant distribution, then this distribution is the same up to scaling. So that's a theorem of Misha Sodin. Anyway, so they look at this function, which actually I'll write the formula for this function. So it's so the an are Gaussian coefficients. So the an here are independent complex normal variables. So this is
With the same variance?
all with the same variance. Thank you. Yes, all complex with say variance 1 Gaussians. And as you look at this series, okay, and then they were able to look at an allocation given by this potential. So, so although the set of points for a probabilist looks much more complicated than than uniform points, the potential is much simpler because instead of being given by some series, it's just the log of an analytic function with this quadratic correction. And now we were interested in uniform points. Unfortunately, if you try to do gravity in the whole plane, the force of gravity, natural two-dimensional gravity, the force doesn't converge. So you write down a series and it diverges in all senses. With Shurav Chatterjee, Ron Peled, and Dan Romick, we analyzed an analogous process in RD for D at least 3. So you can take a Poisson process in space and just define the corresponding gravitational potential or gravitational force. Actually, the force converges in all dimensions from 3 higher, the potential only in dimension 5 and higher. And this, and then analyze the domains that arise. It turns out that they have exponential tails on their diameter, which is quite efficient, much better than you could get, say, from the stable allocation. But we couldn't do it in 2 dimensions. So in 2 dimensions, the way we can do uniform points is just work in finite volume where there's no problem of divergence. So that's what we're doing here. Okay, so that's the one you saw before. So one application of gravitation. So I will explain this theorem on gravitational allocation I stated. So I'll explain the idea behind this in a few moments. But let me, before explaining this, say why, how it is applied. So sorry, let me go back to where we are. So one application is to matching, to the classical matching problem. So given n red points and n blue points on the sphere of area n, we want to match them. And we can use gravity to define a matching where the expected average distance of the matching is root log n. So x here is the average distance between a point ai and what it's matched to, on a red point and where it's matched. And the theorem of Aitai, Komlos, and Tusnadi tells us that up to the value of the constant, this is optimal. Okay, so how does this go? So we have blue points and red points. Let's put down the blue points and think of them as stars. Now the red points will arrive one by one. When the red point arrives, just apply the force of the gravitational potential to that point. Look at the gradient flow we defined. It's going to be matched to some blue point. Do this matching and repeat. So one key point is after the first blue point is gone, the remaining n-1 points are independent uniform points on the sphere. We haven't created any bias. Contrast, maybe a more natural thing to do in the first step would be to match A1 to the closest blue point. That's more natural, but it actually creates a bias. So after you do that, you tend to go for the point where with the largest Voronoi cell that has a preference. And so the points get biased. But with gravitational allocation, the points don't get biased. And after the first matching, we have n-1 points, which are still independent uniform. Anyone sees why?
Point to be moved was uniform?
Right, because of the equal area. So the equal area tells us that the first red point is equally likely to be matched to each of the n blue points. So we're taking n uniform points and just sampling one uniformly at random and removing it. And now it's easy to see that that just leads to n-1 independent uniform points. So now we can repeat. And in the first, by the allocation theorem, we got root log n in the first round. In the second round, we have to have a correction term because the theorem of root log n allocation was on a sphere of area n with n points. Now we have a sphere of area n, but only n-1 points. So we have to scale the radius by square root of n over n-1 to map area n-1 to area n. And we can repeat this again and again. And in the end, what's the average distance? We're going to get the 1 over n. Right? What's this average distance, expected distance? When we're down to k points, we basically get root log k. I'm adding a 1 here just to take care of the case k equals 1, but it's basically root log k. So we just have to have this average, and with the scaling factor root n over k to take care of the different radii. And this is an easy series to sum. You can take out the root, just bound this by root log n, and you'll see that the whole thing is bounded by constant root log n. So you get the claimed average. Now this matching algorithm has an advantage, which is also a disadvantage, namely it's online. So where a point gets mapped only depends on where a red point gets mapped only depends on the previous red points and all the blue points, but not on the later red points. So here I want to emphasize again the open problem, which was for the greedy matching. So for greedy matching, as in work with Ander Holroyd, Robin Pimentel, and Oded Schramm that appeared in 2009, we got a tail bound for the distance in the greedy matching, which when integrated gives an expected average distance, which is about n to the quarter. I expect conjecture that the true average is order log n. But all I know is the lower bound root log n, which we have for all matchings, and the upper bound that you see here. Problem is also open in higher dimensions to understand the greedy matching, although the fair allocation is the optimal matching is understood to great precision, and you'll hear some more maybe in Michel's talk. Okay, so in the remaining 8 minutes, I want to tell you something about the proof for the allocation theorem. So expected distance root log n. Let me sketch why that's reasonable. So the key thing is to understand how large is the force on a typical point. So let's understand the variance of a force on a typical point. So because of the symmetry, if we have a typical point y on the sphere, the expected force on it is 0. So we want to understand what's the second moment, or equivalently the variance. And so let's divide this area around it to rings, concentric rings. So this is a ring at distance k. And so for each k, let's look at the contribution of the force of stars at distance k. So since we have 1 star per unit area, there are about k stars in this ring. Let's take a unit of area here where the number of stars is approximately Poisson 1 in this unit of area. They're all at distance about k from y. What's the force? Well, because this is 2-dimensional gravity, the force is 1 over distance, not 1 over distance squared. So force will be of order 1 over the distance, but it's multiplied by the Poisson number of points that fall in this region. So the variance of the force here will be order 1 over k squared. Second moment will be 1 over k squared. And the contributions from different regions will be essentially independent because of this approximate Poisson property. So overall, the contribution of this ring to the variance will be 1 over k. We have to sum k contributions like this. And now when we sum this over k, we're going to get a log contribution for the second moment. This tells you that the second moment is log n. From here, you could believe, but it's not obvious, that the typical size of the force is root log n. Now, one exception to the typical size is if a point y happens to land near a star, say less than distance, small distance from a star, then the force on it will be bigger. But for the local force to dominate the global force, the star has to fall quite close, less than distance 1 over root log n. Okay, because the global force from the faraway stars, which we've computed, is order root log n. So this comes in. So now let's take a typical point, now I'm calling it x, and see what's going to happen to it in its travel. So typically it's not immediately near a star. So it starts traveling with the force and approximately along a straight line. Occasionally, a star that's not too far is going to curve it a little bit. So again, the force is root log n. When is this point going to be swallowed by a star? Well, only when its local force dominates the global force, which means only when it's within this strip of 1 over root log n around its path. And since the points are approximately Poisson of rate 1, this will happen when this strip has area 1. So the strip has area of order 1 after you've gone a distance of root log n, because it's a strip of width 1 over root log n. So that's why, so the point will travel until accidentally there is a star close enough to its path, and then it will just veer and fall into that star. And that distance is going to be root log n. So you can also see this from, any questions here about this heuristic? Okay, another calculation which is kind of closer to the rigorous proof starts with this formula. So psi of x is where x is allocated, and that's x plus the integral of the force over the path. Now, the magnitude of the force, we said, is order root log n. So in order to handle the distance, we want to know that the time until absorption is order 1. So the time, we have this differential equation that boundary absorption. And here's a really beautiful fact that follows from a principle called Yuval's theorem in mechanics, which says that the time to absorption has exactly an exponential distribution with parameter 2 pi. So this is exact. It's not approximate. It's not asymptotic. And it's true no matter how you put the points down. So it's not just for random points. So it's OK, so to get this for fixed points, you have to pick the starting point at random. But in our setting, we're fixing x and then picking the points at random. And we get this fact. And this fact, I don't have time to go into details, but it follows from Yuval's theorem that gives a differential equation for the volume of the image of a region under the flow. So the derivative of the volume is given by the integral of the divergence of the force. And when you write that down, you get the exponential, you get the differential equation for an exponential. So and the paper is on the archive if you want to see more details. But actually, you can use this principle to give another proof of the equal area theorem that I alluded to in the beginning. And the advantage of that proof is it doesn't need to use any piecewise smoothness of the boundaries of the basins, which I implicitly alluded to in the previous proof. And so the bottom line is, using an argument from differential equations, we get this beautiful fact that the time to absorption exactly has an exponential distribution. And then if you use this, you again get the root log n. So let me connect to something closer to what you'll hear from Michelle after the lunch. So if instead of L1, you look at L2, there's been influential physics paper by Carioculu, Lubucello, Parisi, and Sicuro, and they gave detailed conjectures with heuristic reasoning why when you average the squared, so this is like a W2 distance in a matching, this should behave, I'm going to focus on the two-dimensional case, so it should behave like 1 over 2 pi log n. You see, we know that the average of the optimal matching is root log n, so that suggests that the average squared should be log n. It doesn't prove, just suggests. But in fact, they came up with a conjecture for the constant, and this conjecture was proved by, for d equals 2, by Ambrosio, Stra, and Trevisan. So they established this 1 over 2 pi here rigorously for the optimal matching. What's most interesting for us is their analysis suggests, but doesn't prove, that gravitational allocation will also achieve this asymptotic optimal constant. So although it doesn't seem to be optimal for W1, it does seem to be optimal for W2. Unfortunately, as Ambrosio et al. Write, their proof doesn't actually analyze any specific coupling. So they use gravitational allocation as part of the argument, but in the end they use duality in a way which doesn't prove that any specific coupling has the right property. It just using duality proves the optimality. So there's some delicate interchange of limits going on, but as I said, their analysis suggests that actually gravitational allocation will match this optimum. So basically, I'm almost done. I want to just show you final slides that this kind of gravitational allocation can be considered in the hyperbolic plane, and there's a beautiful work that's been in progress for the last 5-6 years by Ding and Peled that analyzes this in the hyperbolic plane. And I'll just end with these pictures and again emphasize the open problems. So so I told you about the greedy. So one final open problem. Suppose that so for matching we used gravitation, but the most natural way to do a matching which is related to gravitation is electrostatic. So think of n red particles, n blue particles, put the same forces, but think of them as electrostatic. So red points repel each other, and similarly blue points repel each other, and blue and red attract. And I don't have a simulation of this, but actually I have seen one where the points beautifully travel. So the red and blue create a matching. So when a red and blue point coalesce, their charge becomes 0, so they stop attracting or repelling any other point. And so you do get a matching, and I would conjecture that this matching is of the optimal order. There's no rigorous analysis of this at all, and the difficulty compared to the gravitation is here we crucially use the fact that the stars applying the gravitation were all located at Poisson points or uniform points in the analysis I showed you. While for this electrostatic story, the points, once they start traveling, we don't understand their distribution, so we don't understand the distribution of the forces. And so it's completely open to analyze that kind of, I think, very appealing matching. Thanks for your attention.
What's known about the boundaries of the region? You know all kinds of things, or?
So there's some information on like the number of saddle points there. They are known to be piecewise smooth from classical ODE theory.
Enough to do what?
Enough to do, yes. Yes.
It seems to me that you indicated that when the number of points is large, then the region seems to be elongated.
Right.
Is there either simulations or conjectures what happens when the number goes to infinity? How these shapes would?
Well, remember these shapes are normalized to have area 1, yet the average distance traveled from a point to the center is root log n. So that already gives you some elongation.
But would they be straight or?
They will not be straight. But I don't understand, we don't understand exactly. And in particular, we don't understand at all their diameters. So we understand how far a typical point distance. But these things, in higher dimensions, we understand the diameters of the region. But in 2 dimensions, we only understand kind of the typical distance. And the problem is that these regions have tiny tails that go very far and curve around. And we have no control over the actual diameters. Only about the typical distance that the point travels. Yes?
Is this still true for non-uniform three-dimensional shapes? Or non-classical, I guess?
So,
What was the question?
Is the fair allocation still true for non-uniform shapes? Like the torus sphere, I think you showed the hyperbolic.
right. So you can do this. So if you have no boundary, then it's still true. So this extends to. Right. So the key is just to define a potential whose Laplacian is the difference between the empirical measure and the target measure, which is the uniform distribution. Yes.
Do you think there is a gap between those local processes and the optimal matching?
A
Or-
gap.
Yeah. Do you think that there could be such a simple process that matches the optimal constant? Or that those local processes
So again, for W2, I conjecture the gravitational. For W1, I think there won't be a gap. So, but it's okay. Let me be more careful. I think that you can approximate. So, unlike the case of this Gamarnik Sudan, which maybe you're thinking of, here I don't expect there'll be any gap. But it doesn't mean that there'll be a local that will achieve the constant, but there'll be locals that will approximate the optimal constant. But I don't know that for a fact.
This one, for instance, or
So the gravitational, it
no,
seems to
electrostatic.
electrostatic. Wow. I mean, there we have no estimates at all. So no, I don't expect it to be the optimal constant. But prove anything about it. Yes.
Electrostatic, isn't there two questions? I mean, you want to let the blue and the red points both move, right?
Right.
But it would make sense to keep one of them fixed and let just the other ones move. Like thinking of sticking cables in like in DLA or
So then, so let the other ones move. So then it's this, close to this gravitational, but you're adding the repelling force. Yeah, that. Yeah, I think that's fairly natural, and I believe that it can be analyzed by similar methods, because the points applying the gravity are uniform. But it's not something we've explicitly done, so I think that's very natural to do. Thanks.
We should thank the speaker.
All right. So